Thank you. Good morning, all. And I'll be presenting already a published study. Sorry that if it's not new for you. And it's very drastic about Amazon dieback. And I'm presenting on behalf also of my co-authors are here. And those people whose names are underlined are present in the workshop. So please talk to them if you have a chance. And so I don't need to say how important the Amazon is. So it is the largest rainforest, and it has a lot of biomass, which means a vast storage of carbon. So it's important for the climate. But also it has two stable states, so it can be either rainforest or degraded savanna. And so there are two paleoclimate observations show that it has two stable states. And well, on the news in recent studies, we also see that there is increasing risk of droughts and heat waves in the Amazon region. I'm just showing some examples here. So, and this raises a question whether Amazon is approaching dieback. So there are different now MIPs, new MIPs going on, like CMIP, WATF-MIP, that also try to answer this question. But we made use of already existing simulations of CMIP5 and CMIP6 Earth system models, and took advantage of the long-term, extended up to the 23rd century, RCP85 and SSP585 scenarios. Why those scenarios? Because they have really large climate change impacts. So exactly what we need. You can see on the right panel here that CO2 concentration increases beyond 21st century up to 2000 ppm. So it's quite large. And the question we ask is why, where, and how the Amazon dieback may occur. So we used 6 CMIP5 and 6 CMIP6 models that have that have these extensions, and 9 out of 12 of system models actually project the dieback. First, how do we identify this? What is dieback criteria in our study? We just looked at initially very high this GPP or photosynthesis grids in the initial state, so rich biomass, rich photosynthesis grids, and then looked at the grids which have up to 80% large drop of this gross primary production by the end of 23rd century. And in 9 models, you can see white dots show these dieback grids identified. And well, you can see that spatial variation and also scale varies among the models, but the end point is that out of 12 models, 9 project this dieback. And then looking at the timing of the dieback, you can see here this gross primary production, this dieback indicator, plotted against year and global warming levels. And like on the left panel, you can see that dieback happens beyond the 22nd century in most models, but actually this drop starts already within this 21st century under high-emission scenarios. So it's not that far. And for the warming levels, the discrepancy is even larger. You can see that some models project dieback already starting at 1.5 degrees, while others, you need 10 degrees of global warming for the dieback to occur. But, well, the mean value is 5 degrees, which is more optimistic than the multi-line evidence suggests. So models are more optimistic than other lines of evidence, I could say. And then looking at the mechanism of Amazon dieback, here are the plots of the isolated dieback grids areas, GPP, or gross primary production on those, plotted against precipitation, y-axis, and then surface air temperature. And red values indicate high GPP, while purple, bluish colors indicate low GPP. So you can see that this change from red to purple is diagonal in most models, meaning that both precipitation and surface air temperature matters. But in 2 particular models, CAN ESM5 and MIROC ES12, this change is kind of vertical, meaning that mainly surface air temperature, not precipitation, drives the dieback in these models. And for the mechanisms for the climate drivers of the Amazon dieback, well, honestly, it's divergent among all the models, but we just could identify general patterns. So in most models, we can see that warming causes AMOC weakening, and you can see it on the panel on the top right. And this AMOC weakening causes southward shift of this tropical rain belt, ITCZ. And you can also see it in the diagrams below. So this rain, red, goes south downward, which causes hot and dry, especially northern Amazon. In addition to this, we have not only climate drivers, but also large CO2 increases in these high-end scenarios. But CO2 increases, it not only increases CO2 fertilization effect, but also encourages closing stomata, which causes decrease in evapotranspiration, and then causes a decrease in water recycling, and then hot and dry Amazon again. In addition, we identified that by the end of 23rd century, most models project so-called El Nino-like warming conditions, which also, in their turn, lead to hotter and drier Amazon. So even so, at the end, climate becomes no longer suitable for rainforest in most models. Here I'm showing example of 4 models, and we looked at the Copenhagen climate zones from these climate projections at the 21st left and 23rd century, and you can see that this bluish color, which indicates tropical climate, turns to the red arid climate. So even without looking at carbon cycle, the climate is just not longer supporting Amazon rainforest. But sorry for this complicated figure in this slide. I'm just showing it as example of one model. So how about ecosystem processes? We see that in all the models, before this GPP black line drops, we have a large decrease in precipitation, large increase in the temperature, which either coincide or precedes GPP drop. And so these are the main drivers again. But the more accurately saying, more specifically, the mechanism will vary among models. So it's both increase of maintenance respiration with warming, then different physiological thresholds of photosynthesis, increase in tree mortality, increase of fires, decrease of nutrient transport, and so on. So it differs among models. But also in these scenarios, we have again high CO2 concentration, which actually starts to decline beyond 21st century with this gray line. And because of CO2 growth decline, it also it means less boost for photosynthesis, which also contributes to the dieback. Finally, these considered RCP85 and SSP5 scenarios, they have some land use change, but it actually finishes before 21st century, as I show in this small figure on the right. So land use change emissions already in the Amazon area peaked, but still we find that in the dieback areas, there is large increase in some models to the of the forest converting to the crops or other land use styles, but also in most models projecting dieback, we have primary vegetation turning to the secondary vegetation in the dieback grids. So although in these scenarios we cannot say that land use change is the primary driver, we could identify that it also contributes to the dieback. So I'm coming to the conclusion. First, we identified dieback in Amazon in most models, CMIP5 and CMIP6 models, which with a variation in of scale and spatial pattern, but it all starts within the 21st century in the majority of models. Then temperature, precipitation, land use change are key factors reducing the Amazon resilience. And looking beyond, so what are the impacts of the Amazon dieback on the climate and carbon cycle? In this considered concentration-driven runs, we couldn't find much, but if you look at this right panel of this figure, you can see that, well, in Amazon dieback grids, there is quite some, up to 0.5 gigaton per year drop of ecosystem carbon uptake by Amazon. So it potentially it would have the large impact on the, even in the models, on the climate and carbon cycle. So thank you for the attention. Here I'm just outlining the climate drivers land use change ecosystem processes that were identified in the models, and the study QR code can be found below. Thank you.
While we're waiting for folks to line up at the microphone, there are two questions online which are essentially the same question. One is phrased, how much of these results may be influenced by the fact that most CMIP models simulate lower than observed present-day precipitation over the Amazon? So what's the role of present-day biases in precipitation over the Amazon?
I can say that it's quite large. And in this figure particularly, you can see we have black dots indicating present climate represented by ERA 5. So not all the models, but some models indeed have large biases in the Amazon region for precipitation. So this will of course impact the projections, but we try to not exclude models based on this because we wanted to really dive into the mechanism of the dieback in the models.
Okay, coming back to the room. So question, okay, you can.
Yes, Irina, hi, thank you. That's great talk. I have this question. So you show a warming level of 5 degrees where this is the dieback is starting in the models, but you looked at only at the 8.5 scenario.
I did, yes.
So presumably, in some models do have weakening of the AMOC even at lower scenarios, so that could potentially lower the warming level if you looked at, let's say, the 370 scenario.
I agree. I would like to do it. The problem is that most scenarios do not have extensions up to 23rd century, which are needed for, well, models require time for the dieback. I looked also, well, I'm currently looking at SSP 1 to 6 scenario, which has extensions. Well, the changes are not that dramatic, fortunately or unfortunately.
Yeah, yes. That's too low scenario. Yes. Yeah, but maybe the 245 and the 245 at least has extension. So, yeah. Anyway, okay, thank you.
Yeah.
So next question.
Yep, thanks, Irina. Couple of questions I'll bundle into one. So you mentioned precipitation. I wonder whether it's precipitation variability that's more important than mean precipitation.
Oh yes, well, it's really a mess among the models. Unfortunately, not only precipitation, but also present-day gross primary production is also varies among the models. So like, those are, well, we can say those are projections, but biases are large, yes.
Okay. And then I wondered if there was any way of, if you tried stratifying these by, models that have interactive dynamic vegetation or that have fire on, fire off,
yes.
and whether any of these make any difference.
I tried at some point, so one model, UK ESM, has dynamic vegetation and we identified large-scale dieback, but the other model, CMIP5 MPI, which also has dynamic vegetation, it didn't project any dieback, although it had drop of GPP, but just not enough. So right. We couldn't make a clear line.
Yeah. Well, clearly our model's the right one.
Yes.
Very much.
Yeah. Last question.
Cool. Thanks, Irina. I'll just ask one question, but I'd love to talk more about this. But yeah, on your threshold diagram where you've got temperature and rainfall, of course, CO2 actually doesn't just fertilise plants, it changes their water use efficiency. So if there's a threshold, then that threshold itself moves. So at high CO2, you would get a different threshold diagram. So the high CO2 protects the plants at some stage from the, climate. Are you able to separate out that effect? Because your Köppen classification doesn't move in time, obviously, whereas with high CO2 it might do.
If I'm understanding, so can you repeat the question?
So if you've got a threshold in temperature and rainfall space, at high CO2, that threshold would be different.
It does, but at the end there is for some models we identified really solid threshold, like 35 degrees grid warming or 45 degrees, for which even increasing CO2 will not tolerate the. Will not help anymore. So at some models we really found this drop after some threshold.
maybe later you can
Yeah.
discuss.
Yes.
Okay,
Thank
cool.
you
Great
so
talk.
much.
Thank you.
Thank you.